Calculus Day 2930, Unit 4. This is part 3 of the notes. We're working on related rates. So the next problem, a stone is dropped into a calm body of water, causing ripples in the form of concentric circles. The radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so let's identify what parts of the question are going to be important to help us figure this out. So the radius is increasing at a rate of 1 foot per second. So really just the 1 foot per second. That is dr dt. They tell us here the radius is 4 feet. And again, I don't even need that. You just need the radius is 4 feet. And we want to know what is the rate of the total area. I'll write that over here. So, hey, that's dA dt. Okay, identify all the variables involved in the problem. So all we're dealing with is area and radius. Identify which, if any, of the variables in the problem remain constant. And no variables are constant. Okay, and now identify the rates that are given and the rate that we wish to find. So I know the dr dt, which is the rate at which the radius is changing with respect to time, is 1 foot per second. Let me go up so you can actually see the problem again. And which one are we trying to find? Well, that's the very last one, and it says at what rate is the total area changing, so the rate at which the area is changing. We don't know. I know area is two-dimensional, so it's going to be square feet per second. Okay? And let's use this information to help us do 4 through 6 on the next page, well, bottom of your page. So write an equation, hey, area of a sphere. And again, that's part of the key here is that I know it's going to be, excuse me, not area of a sphere. We're doing area of a circle. Let me do that again. I need my eraser to come on. There we go. Area of a circle, because they were talking about concentric circles. What does concentric circles mean? It's kind of like a bullseye. So the rock hits, and then the waves start, the ripples start going out and out, and those are supposed to be perfect circles. So I'm doing area of a circle, and what's the formula for area of a circle? Area equals pi r squared. So number 5, hey, let's implicitly differentiate both sides of the equation. So this derivative of a is just going to be 1, but then I got to do dA dt because with respect to time. Pi is a constant, so I'm going to take this 2, multiply out front, 2 pi r to the first, but then I have to take the derivative of r with respect to time. And now let's substitute in what I know. I know the radius is 4. Let me change my colors here. Let's go to blue. So I don't know. We just said number 3 that I'm trying to find the rate at which the area is changing. I know pi is a constant. I was told in the original problem the radius is 4, and I was also told that we're looking at the instant when the rate at which the radius is changing is at 1 foot per second. Okay, so there's 4 feet times 1 foot per second, so feet times feet would be square feet, which, hey, that's what we want our area to be in, and then it's going to be all over second. So the units should match up as well. So the rate at which the area is changing, 2 times 4 is 8, so it's 8 pi, and again, as I just said, that's going to be square feet per second. Okay, and let's go on to the next one. Okay, water's leaking out of a cylindrical tank at a rate of 3 cubic feet per second. If the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? So this is just a cylinder. It's like a soda can. And I apologize for my artwork. Oh, that's got to be a circle there. Okay, so what do we know here? 3 cubic feet per second. What does this represent? Again, that's the amount of water coming out. And again, cubic, once I hear cubic, I'm thinking volume, and that's the rate at which the volume's changing. Here I have 4 feet. Again, they kind of gave that away. Hey, that's my radius. And at the end, what rate is the depth of the water changing? This is going to be the height. So it's the rate at which the height is changing. Okay? So whenever I'm dealing with volume of a cylinder, what are the variables? Are we dealing with volume? Are we dealing with radius? Are we dealing with height? Well, hey, they told us something. They said the radius of the tank is 4 feet. So that's going to be constant. So that's going to be helpful. Radius is going to be equal to 4 feet. Label that 4 feet. And then what else do I know? Well, what are the other rates? I was told the rate at which the volume is changing is 3 cubic feet per second. And here's where I got to pay attention because it's obviously going down. So it's negative 3 cubic feet per second. And what am I trying to find? I'm trying to find the rate at which the height of the cylinder is changing. I don't know what this is, but height is going to be, again, that's one-dimensional. It's going to be feet per second. Okay, so let's take this information. Let's go on to the bottom of the page. Write an equation. So the volume of a cylinder, volume equals pi r squared h. Okay, and the nice thing is, and it says substitute any value that represents a constant. Well, they told me radius is going to be 4, so let's put that in now so I don't have to even deal with it. So volume equals pi times 4 squared h. And now I'm going to get volume equal to 16 pi h. Okay, and now let's implicitly differentiate. So derivative of v is 1, but with respect to time it's dv dt. Derivative of 16 pi h is just going to be 16 pi, because the derivative of h is 1, but then I got to take dh dt. And now let's substitute in what I know. And I know dv dt we said was negative 3, 16 pi dh dt. And now I can solve this for dh dt, which is what I'm trying to find. So I take this, and let me just change the color of the pen here. Divide both sides by 16 pi, and we're not going to change this. We're going to leave this as dh dt. It's the rate at which the height is changing. And those cancel out. It's going to be negative 3 over 16 pi. Okay? So that's the rate at which the height of the cylinder, which is losing 3 cubic feet per second, and when the radius is 4, this is what the height is changing, the rate at which the height is changing. Okay, and again, the height's going to be going down. Okay, let's try the last one. Okay, so a cone has a diameter of 10 inches and a height of 15 inches. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second. At the instant when the radius of the exposed surface area of the water is 2 inches, at what rate is the volume of the water changing? So let's look at what we have for given information. So first thing here is, what do we got? Oh, the original cone has a diameter of 10, which again, we want to think of that in terms of radius, but in a height of 15. Now, water is being poured into the cone, so the height of the water is changing. Again, height of the water level is changing at a rate of 1.2 inches per second. So this right here is going to be, again, the rate at which the height is changing, dh dt, at the instant when the radius of the water is 2 inches. So that's going to be the radius. And then what do we want to know? what rate is the volume changing. So there's dV dt. Okay, so let's draw a little picture here. So I have some cone. That's not too shabby. So again, they give us the original um, diameter, but we want to talk in terms of the radius, and then there's the height right there. So there's the height. I'm sorry, right over that. There's the radius. But there's going to be some water in it that we're pouring in, so the water is going to be right there and everything down below, and that's going to have some information that we have to know as well. And actually, one thing they do in the original cone, they told us diameter is 10, which tells us the radius is 5, the height's 15. So in that original ratio, the ratio of the radius to height is 5 to 15, which is 1 to 3, and that might help us later on. It's going to be times where we're not going to know to do that up front. We'll figure it out as we go through the problems. All right, so what do I have? I'm dealing with radius, volume, and height. Um, any in the problem that remain constant? There are none. And what do we know? Let's go back up. Sorry, I keep scanning down. So I know the rate at which the height is changing. That's the dH dt. dH dt. And you're pouring it in, so it's getting bigger. So that's 1.2. In this case, it's inches per second. What don't we know? I don't know the rate at which the volume is changing. So dV dt, I don't know what that is. And that's, again, volume is going to be cubic inches per second. And that's what we're trying to find. So let's go to the next page. 4, 5, and 6, write an equation, and we can flip back and forth as we need to. Well, we're talking volume of a cylinder. So 1/3 pi r squared h. Okay, so what do I know? I know, um, as I said before, that the ratio of the radius to the height was equal to 1/3. So let's multiply both sides by h, so I get radius equals 1/3 height, because I only want this in, I'm only going to want one unknown at the very end. And if I had this, I'd have too many unknowns. So if I can relate those two together, then I will. So now let's put in what I know. So volume equals 1/3 pi r squared h. Every place I see a radius, I'm going to substitute in 1/3 height. So volume equals 1/3 pi times 1/9 h squared times h. So all we're doing is we're just relating this to all, putting it all in terms of height, volume in terms of height. 1/27 pi h cubed. And again, that's all from our relationship between the radius and the height. Okay, so now we want to implicitly differentiate. Derivative of v is just 1. So dv dt. And then 1/27 pi h cubed. So I'm going to multiply that by 3. So I'm going to have 3/27 pi h squared. And then I have to take the derivative of h with respect to t. 3/27 ends up being 1/9. So the rate. So now let's simplify and substitute in what I know for the height and dH dt, the rate at which, so I don't know the rate at which the volume is changing. That's 1/9. That's pi, and I'm going to leave that there. The height is 6, so we get 6 squared. And then the rate at which the height was changing, we said was 1.2. So now I'm going to use my calculator, and we can figure this out. So with my calculator, 6 is the height in inches, 6 squared, that's going to be inches squared. This is the height, the rate at which the height is changing, that's in inches. So inches squared times inches is going to be inches cubed, which matches up with my units of volume. So take the calculator. Now normally we'd either leave it all as decimal, we'd leave it all as decimal, or we'd leave it as an integer with a pi or fraction ratio either way, but this is fine for now. So 4.8 pi cubic inches per second. Okay, that's going to be it for part 3. We're going to have some other problems that we're going to talk about in class, and I'll eventually put the solutions either onto a video or onto the Google Classroom that we can look at. All right, great.